The next component to study in more detail is the nucleophile. Nucleophiles and bases are similar because they both contain a lone pair or a pi bond. However, they differ in the way they attach, or in other words, in the way they donate their electrons. Bases donate electrons to protons, as shown here, whereas nucleophiles donate electrons to an electron-deficient atom, called an electrophile, which is usually a carbon atom, and that is again shown here. Be sure you are able to clearly state the difference and understand how they donate their electrons in a different manner. To look at it in more detail, follow along with me. This slide states the major differences between basicity and nucleophilicity by way of definitions. Although nucleophilicity and basicity are interrelated, they are fundamentally different. Basicity, defined as a measure of how readily an atom donates its electron pair to a proton. It is characterized by an equilibrium constant, Ka, in an acid-base reaction, making this a thermodynamic property. Nucleophilicity is defined as a measure of how readily an atom donates its electron pair to other atoms. Nucleophilicity is characterized by a rate constant K, making this a kinetic property. Now there are some parallels between nucleophilicity and basicity. 3 instances are pointed out here. Read this together with me, beginning at number 1. For 2 nucleophiles with the same nucleophilic atom, the stronger base is the stronger nucleophile. The relative nucleophilicity of hydroxide and acetate is determined by comparing the pKa values of their conjugate acids. The conjugate acid of hydroxide with 1 extra proton is water. That has a pKa of 15.7. The conjugate acid of acetate with 1 extra proton is acetic acid. That has a pKa of 4.8. This means that hydroxide is a stronger base and a stronger nucleophile than acetate. Number 2. A negatively charged nucleophile is always stronger than a nucleophile, is always a stronger nucleophile than its conjugate acid. For example, hydroxide, which is negatively charged, is a stronger base and a stronger nucleophile than water, which is neutral. Number 3. Right to left across a row of the periodic table, nucleophilicity will increase, basicity increases as well. That is shown in the trend at the bottom. I do want to point out a difference between nucleophilicity and basicity regarding steric hindrance effects. Let me begin by defining steric hindrance, which is a decrease in reactivity resulting from the presence of bulky groups at the site of a reaction. Steric hindrance will decrease the strength of nucleophiles, but does not decrease the strength of bases. Even sterically hindered bases, which would be poor nucleophiles, are actually called non-nucleophilic bases. Some examples are shown down at the bottom. Now is a good time to branch into solvents and still continue a discussion of nucleophiles. We know that most organic reactions are performed in the lab in a liquid solvent. That solvent will need to be able to dissolve the reactants. Substitution reactions use polar starting materials, so since like dissolves like, then polar solvents are used to dissolve them. There are 2 types of polar solvents, protic and aprotic. Note that the strength of the nucleophile can be affected by the type of solvent used. Polar protic solvents solvate both cations and anions. For example, if the salt sodium bromide is used as a source of the nucleophile bromide in water, then the sodium cations will be solvated by water molecules, and the bromide anions will also be solvated by water, but in a different fashion. Focus on the image to the left. The solvation occurs between opposite charges. Since sodium is positive, then it is the partially negative oxygen interacting with the positive sodium. Looking at the image to the right, it will be the partially positive hydrogens interacting with the negative bromine. This solvation traps the ions of the salt and allows for the salt to dissolve. The interactions here are between a dipole of water and the ions of sodium and bromine, and is called an ion-dipole interaction. Note that as the water is removed or evaporated, then the sodium ion and bromide ion would be able to interact again and then reform the solid. There will be a trend for nucleophile strength here. As the size of the ion gets larger, then the strength of the nucleophile goes up. This is the opposite trend of base strength. Here are 5 polar protic solvents. These are very common polar protic solvents. Please make note cards of them, and you can easily remember their identities. Polar aprotic solvents, the term aprotic means without a protic portion, without a proton attached to an oxygen or nitrogen. Because these solvents are polar, they will still have dipole-dipole interactions, but there will not be any hydrogen bonding like we saw with water on the last slide. There are 6 common example polar aprotic solvents here. Make a note card or note cards of these as well. If you know the most common protic and most common aprotic solvents, it will be easier to identify the types of reactions later. The nucleophilicity, or strength of nucleophile, increases in a polar aprotic solvent. This is because the cation portion of the salt will be solvated using dipole-dipole interactions. See the sodium cation on the left side of the screen and how it is solvated by the solvent. The solvent here is acetone. The hydrogens, or protons as they are commonly referred to, will not participate in the hydrogen bonding. This means the bromide will not be solvated. It's illustrated by this picture on the right. This allows nucleophiles that are negatively charged to be more reactive, since the positive counter ion is trapped and the negative nucleophile portion is free. The nucleophilicity for polar aprotic solvents will be opposite to what you saw for polar protic solvents. The reverse trend is shown on this slide. I mentioned earlier that nucleophiles can be negative or neutral with a partially negative charge. Here are some common nucleophiles. Don't memorize them, but instead memorize that common nucleophiles will contain one of the following atoms: oxygen, nitrogen, carbon, one of the halogens, or sulfur. Let's start to relate nucleophiles back to organic reactions now, specifically substitution reactions. In a substitution reaction, there are 3 possibilities. Focus on the general reaction at the top as I mentioned them. Bond making and breaking could occur at the same time, or bond breaking could occur first, and the third possibility is with bond making occurring first. Those 3 possibilities are stated here. We will now examine each of the 3 possibilities individually. The first stated that bond making and bond breaking occur at the same time. Focus on the reaction mechanism. It is a mechanism because it is using curved arrows that show the flow of electrons. This situation happens in one step. It is a type of a bimolecular reaction because both components affect the rate of reaction. The rate is overall second order. The second possibility is for the bond breaking to occur before the bond making. A mechanism of this scenario is shown. Focus on the mechanism. This process would require the leaving group to break off the alkyl halide, forming a carbocation, which is in the middle. Then, in a second step, a nucleophile approaches and forms a covalent bond with the carbon bearing the positive charge. The rate determining step in this process will be the first step. This rate is only dependent upon the concentration of the alkyl halide, and this time is just first order. The third possibility is for the bond making to occur before the bond breaking. This would require the nucleophile to donate electrons to the partially positive carbon and forming a covalent bond. Notice how this would put 10 electrons around the carbon, as shown in the middle. Because this pathway violates the octet rule for carbon, it is not a reasonable mechanism. This third possibility can be eliminated. Now that you know the two reasonable possibilities, we can look at each in more detail. Consider the example reaction shown here. It consists of bromoethane reacting with acetate to produce methyl acetate. Can you identify the alkyl halide, the nucleophile, and the product? The alkyl halide contains the carbon-halogen bond, which polarizes the carbon to be partially positive. That makes the carbon electron poor and gives it the characteristics of an electrophile. The oxygen bearing the negative charge has an abundance of electrons, giving it the characteristic of a nucleophile, like we discussed earlier. The kinetic studies of this particular reaction have shown it to be second order. Let's consider a different reaction now. This reaction still has the same nucleophile, but uses a different alkyl halide. Experiments have shown this reaction proceeds using first-order kinetics. There must be something different about the alkyl halide here and the alkyl halide on the last slide. We will look more into this in the next part of the lecture.